Powering civilization requires managing extreme heat, pressure, and intense chemical reactions. But these environments are fundamentally hostile to the materials we use to contain them. For centuries, engineers were forced into a compromise. You could choose a metal that was physically tough, but it would eventually succumb to rust and decay. Or you could select a metal that was chemically stable, but it would be too soft to handle a heavy structural load. This friction between strength and stability is a primary bottleneck for technological progress. To move forward, we need materials that refuse to pick a side. The physical layout of the periodic table places a specific set of elements at the exact center of the transition metals, Group 10. Moving down this column reveals a scaled spectrum, from rugged metals used in heavy industry to fleeting elements produced in physics labs. While these four elements appear different at a macroscopic scale, they are united by a specific atomic architecture that dictates how they interact with the world. This column serves as a roadmap for our journey down the group, showing how a shared chemical structure enables a wide range of industrial applications. We begin at the top with nickel. Of the entire group, it is the most naturally abundant and the most chemically reactive. Nickel's strong metallic bonding makes it a rugged building block. It provides the physical muscle required for large-scale manufacturing and heavy infrastructure. It is an essential component in the stainless steel and rechargeable batteries that define the consumer landscape, allowing for products that are both durable and affordable. Because it is both tough and plentiful, nickel provides the physical foundation for the mass-market goods we use every day. The reason these metals are so effective isn't just their physical strength, but a quantum trait: partially filled d orbitals. These incomplete orbital shapes allow the metals to easily juggle electrons. They can accept, hold, and pass off electrons without destabilizing their own atomic structure. This makes them ideal catalysts. They can grab onto passing molecules, force them to react with one another, and then release the new compound while remaining completely unchanged themselves. This mechanism ensures that Group 10 elements aren't just passive structural supports. They are active controllers that dictate how other chemicals behave. As we descend to palladium and platinum, the atoms become significantly heavier and the metals become drastically more dense. Platinum's physical weight is a signal of its rarity and its specialized nature. It exists in a state of high-density stability that lighter metals cannot match. But there is a trade-off. As their mass increases, their chemical reactivity plummets. These heavier metals are incredibly resistant to corrosion, oxidation, and chemical attack. This combination of catalytic power and extreme durability allows them to function in environments that would destroy nickel. They are used to neutralize toxic exhaust inside high-temperature catalytic converters and to precisely target rogue cells in specialized cancer treatments. Palladium and platinum are the specialized guardians of the group, performing high-stakes work where cheaper materials would simply fail. At the absolute bottom of the column, the trends of mass and density reach a breaking point in Darmstadtium. This element is so heavy and unstable that it does not exist in nature. To create it, we must use high-energy physics installations to force atoms together at incredible speeds. Its existence is measured in fractions of a second. It cannot be used to build a battery or a converter. It serves as a fleeting microscopic proof of the group's chemical logic. Darmstadtium represents the edge of what is possible, proving that the mathematical trends of Group 10 hold true, even at the furthest limits of human discovery.